All right, so up to this point, we've looked at the arithmetic and geometric sequences. And so we have a basic understanding of what they are. The first thing is they're a linear relationship. And we already know that for a linear relationship, I only need two pieces of information. I need my start value, and I need my rate of change. That's it. And all first semester, we were dealing with that. Given the following tile pattern, what's your rate of change? We found it. And then he said, what's your start value? Oh, I take figure 1 and I go backwards with my rate of change. I get figure 0. Done. Start value. Bicycle races, right? We did bicycle races. We did all sorts of things. Well, an arithmetic sequence is no different. It's exactly the same because it's a linear relationship too. The only difference between an arithmetic sequence and a linear equation is that arithmetic sequences are discrete values. You can see the list right there. It's 10, 7, 4, 1. Is 3 in my sequence? No. Is 2.5 in my sequence? No. But if I had a linear equation, those numbers might very well be in my sequence, right? Because then it's all numbers along the line. We don't have a line here. We have discrete points. But otherwise, start value, rate of change. The recursive formula that we're looking at today uses those two pieces of information just like we used them for y equals mx plus b. The recursive formula, though, is kind of a simpler form of an equation, might be one way to think about it. But it generates, it can be used to generate our sequence. It starts this way. T of something, that's my start value. And then, so it's two parts to it. The second part is the rule, and the rule says T of n, which just means the next term, is equal to the previous term, that's what T of n minus 1 is, and then it's going to be plus or minus my common difference, my rate of change. So all I need is the start value, that's this right here, and then I need my common difference, that's that right there, which is my rate of change. Once I have both of those, I have the formula. Pretty easy. Let's take a look for this example. Well, the first thing is the start value. One of the differences between this and a linear equation is the start value here can be any term in the sequence I want. I can start it at t of 1. If I'm really crazy, I can do t of 2. And then if I'm just way out there, I can do t of 3. The problem at starting with t of 3 is I miss t of 2 and 1. So that won't generate the whole sequence, but it'll generate everything from t of 3 on. So keep in mind, you can use any start value you want. By default, we use t of 1 because we're usually given a sequence like the one we see here. And t of 1 is simply the first term in the sequence. Yeah, we're disconnected. So basically, we choose the start value t of 1 by default. It's the first term I see listed in the sequence. For us, in this example, it's 10. T of 1 is 10. I could use anything I want. I can use t of 2, t of 5, whatever. The problem with using those later ones, of course, is that I don't get the whole sequence. Then the rule says, oh, all I need to do is add or subtract the common difference. Well, I have to calculate that first. My common difference, if I go and pair up these numbers, I can see what my common difference is. 10 down to 7 is minus 3. 7 to 4 minus 3. 4 to 1, minus 3. I see a trend. That trend is my rate of change or common difference is negative 3. I'm going down by 3 each time. Now I can modify my formula, and it's done. There's my formula. I got my start value, got my rate of change, and I got my recursive formula. That's it. Doesn't get any harder. Where students typically get caught up is in the t of n and t of n minus 1. N is just a counter. Counting 1, 2, 3, 4, etc. It's just a counter. That's all n is. N is the current number I'm looking at. N minus 1 is the one before it. Make sense? Because if I'm at n, then the previous one must be n minus 1, going backwards. That's the only thing. So now, let's see if it generates my actual sequence. So I've got t of 1, so now I need t of 2. So I'm plugging 2 in for n equal 2. Well, that tells me t of 2 is equal to t of n minus 1. That's the previous one. So 2 minus 1 is t of 1 minus 3. I've got t of 1. It's 10. So 10 minus 3. So t of 2 better be 7. And when I look up top, yay, it's 7. So far, our recursive formula is working. Let's do it again. T of 3. N is now equal to 3. Plug that in. T of n minus 1, that's 3 minus 1, which would be t of 2. And then I subtract 3 from that. But I have t of 2, it's 7. So t of 3 better be 4, and indeed it is. And we could just keep going. The recursive formula keeps generating the sequence. You start at the start value, in this case t of 1, and then you just keep subtracting 3 as you go. And you generate the sequence. Does my start value have to be 1? No. What about t of 0? It's like figure 0 when we did tile patterns. You remember that? Figure 0? Yeah, we could find t of 0, and we can use it in our formula if we want. Later, we're going to need it for the explicit formula. This is recursive. You don't necessarily need t of 0. In the explicit, we will, just like we needed it for y equals mx plus b. But if I want to find it, all I have to do is go backwards, just like we did with tile patterns. If I have figure 1, and I do, it's t of 1, it's 10. Then I need figure 0. I go backwards. Well, if I'm subtracting 3 going forward, I add 3 going backwards. Therefore, t of 0 is equal to 13. 10 plus 3 going backwards. But then the formula is exactly the same. It doesn't change. Only the start value changed. So it's still t of n is equal to t of n minus 1 minus 3. Both of these recursive formulas are valid for this sequence. They just have a different start value. Let's look at recursive when we're dealing with geometric, because we're expanding the equations that we're dealing with. Did a lot of linear. We'll still do linear for sure, and that's arithmetic. But now let's look at geometric. Let's say we have the following. Let's do 2, 4, 8, 16, 32. That's the binary number sequence. Powers of 2, binary. Binary means it's either a 0 or a 1. That means there's 2 choices. Power of 2. You might know it as the doubling, because we did it with the rabbits. Double as you go. How many of you have a cell phone? How much memory you got in yours?
About
100? 128?
Yeah, 128.
Yeah. That's a number in the binary sequence. How about you? What do you got in yours?
I think like 64 or something.
Double 32, you get 64. So the binary sequence has those numbers in it. And every time you deal with computers, their memory is binary. Therefore, the amount of memory you have is a binary number, power of 2. Because there's only two choices, 0 or 1. And so it's showing you how much memory it has by how many of those 0 or 1s you have. Because that's what memory is. It's just a little tiny thing that registers as a 0 or a 1. It turns out it's actually a voltage. +5 plus or minus something, that's considered a 1. And then 0 plus or minus something is considered a 0. That's how your computers work. Anyway, that's a geometric sequence because we're multiplying by 2 each time. What we learned was it's exponential relationship, not linear. But guess what? You still only need a start value and a rate of change. And I was kind of joking with my other class earlier that, yeah, Mr. Soy sounds like a broken record. What do you need? Start value, rate of change. Because that's all you need. And you can get all these equations, all these formulas that you want. We did it with y equals mx plus b over and over again last semester. Still doing it with it. We can do it with this as well. And we can use it to then create the recursive formula. And it looks virtually the same. I need a start value, and then the next term in the sequence is the previous term in the sequence. Except here, it's multiply or divide by a common ratio. Otherwise, it's the same. Arithmetic, we add or subtract. Geometric, multiply or divide. Start value, no different. It can be t of 1, t of 2, t of 3, etc. Doesn't matter. However, if I start at a later value, I don't get the whole sequence. So okay, excellent. All I have to do then is pick one. Well, by default, like I said, we usually use the first term, t of 1. And in this case, t of 1 is 2. Formula's almost done. Now all I need is my ratio. That's where I pair them up again, except this time instead of trying to find the difference, I'm finding the ratio. Ratio, fraction. I take the next number, divide it by the previous number, or the current number. 4 divided by 2, 2. So I'm multiplying by 2 each time. If I multiply 4 by 2, I also get 8. And if I multiply 8 by 2, I get 16, and etc., etc. Guess what? My rate of change, I found it. Now here's the conundrum. There's a lot of names you'll see in math books for the rate of change for a geometric sequence. You'll see multiple. You'll see multiplier. Throw that I in there. You'll see ratio. And then you'll see my favorite, common ratio. Because if you have a common difference, you also have a common ratio. I like common ratio. But guess what? Your textbook, not so much. Your textbook uses this one, multiplier. I don't really care which one you use as long as you know what it means. It's the number that we're going to multiply. And remember, division doesn't really exist. There's really no such thing as division. It's just multiplying with a fraction. I know, we lied to you. Well, you know, we can't give you the whole picture when you're in elementary school. It just blows your mind. All right, so now I have my R, my common ratio or multiplier, and I just put it in there, 2. There's our recursive formula. Let's test it out. Let's do blue. T of 1, I've got. So what I really need is T of 2. So T of 2 is equal to, well now N is equal to 2. 2 minus 1 is 1, so T of 1 times 2. T of 1 is 2 times 2 equals 4. Is my second term 4? It is indeed. Done. Formula's working so far. Let's do one more. T of 3. N is now equal to 3. T of n minus 1, well that's T of 3 minus 1 or T of 2. But T of 2 we have, that's 4 times 2 equals 8. And in fact, that is the third term, and thus it keeps going. Generates the sequence. Recursive formula, that's all it's for. All you need are 2 parts. The first part is your start value. The second part uses your rate of change. So if you can find the start value and you can find the rate of change, voila, you got the formula. The T of n and equal T of n minus 1, like I said, those are just labels. That's just saying, hey, this is the next term we're going to look at, the previous one, plus or minus or times this common rate of change. Here's the downside. If I gave you this and I said, what's T of 100? Yikes. How do I find that? The problem is this. If I want T of 100, I'll plug in n equals 100. Well, T of n minus 1 would be T of 99 times 2. The problem is I don't know what T of 99 is. I don't know the 99th term. Therein lies the conundrum. The recursive formula fails us. The only way to get to the 100th term is to start at the beginning and go until I get to the 100th term. Why? Because the recursive formula requires the previous value to calculate the next one. That's why they invented explicit formulas. We're going to learn that next class. Can I use T of 0 here? Absolutely. Even though it's geometric, we can still use T of 0. That still exists. And to make that, all I have to do is go backwards, just like I did with the arithmetic sequence. In other words, I start at my T of 1, in this case 2, and I go backwards using the common ratio. Well, if I go forward with my common ratio, I multiply by 2. So therefore, if I go backwards, I'm going to divide by 2. Opposite direction, opposite operation. So I take T of 1 and divide by 2. Well, that's 2 divided by 2. T of 0 is 1. The rest of the formula doesn't change. When we do explicit formulas, we need T of 0. When we do recursive, we don't. We usually use T of 1. But you already know that from the tile patterns, right? You know the difference between figure 1 and figure 0. It's no different here. The 0 term is simply going backwards from the first term. At the bottom, T of 2, T of 3. There's some skills here that you need out of what we've done up to this point. So let's review those so that we're all on the same sheet of music moving forward. Well, let's get a sequence here. Let's see, arithmetic. Let's do 3, 6, 9, 12, 15. By now, you should look at that and go, oh, that's easy. Common difference is 3. Hello. It's like I'm counting by 3s, right? Geometrically, let's do the same thing. 3, 9, 27, 81, 243. Now I can't do it in my head. Easy breezy. First skill. Find common difference. But if it's geometric, you're going to find common ratio. Or, as they use in the book, multiplier. Let's do it. We already know how. I just look at the pairs in the sequence and I see how it changes. I add 3, add 3, add 3, add 3. D equals positive 3. Over here, I do the exact same thing, except now I'm looking at the ratio. 9 divided by 3, 3. So I'm multiplying by 3. To get from 9 to 27, 3 times 3 times 3. Common ratio, 3. And like I said, in the book, they call that the multiplier. Because the more words we can make you memorize, apparently that's better. Math is famous for overloading words. And then we throw Greek at you too, because if English isn't confusing enough, let's throw some Greek in there. Right. We're all so fluent in it. But you know, you go up through calculus and you again. Let's proceed. The next thing I need, the next skill I need is I need to use the common difference I found for a recursive formula. And remember, all I need to do is a start value and then my common ratio or common difference. And so for this one, my start value, we always default to T of 1. That's 3. It's the first term right here, 3. And then the formula always is the same. T of n equals T of n minus 1. And then in this case, I'm adding 3. Done. Over here, T of 1, same thing. It's 3. First term right there. And then the formula is still the same. T of n equals T of n minus 1. The next term is equal to the previous term. Except here we're going to multiply by 3. It's the only difference. Arithmetic, geometric. On the test, you got to do that. They're going to give you a sequence just like in this example and say, oh, find the common difference, find the common ratio or the multiplier, create a recursive formula. That's exactly what you have to do on the test. Third skill you need, find t of 0. Because it turns out we're going to need t of 0 for our explicit formulas. But hey, like I said, we've been doing this since the tile patterns. You just go backwards using your common ratio or common difference. If I go backwards from 3, I have to subtract 3. Gives me a t of 0 of 0. For the geometric, I have to divide by 3 to go backwards. 3 divided by 3 is 1. Done. Found both t's of 0s. Just go backwards. And then the fourth thing you got to know, fourth skill, is you got to be able to generate a sequence when you're given a formula. Just like I did back. Well, that's not that hard. Why? Because I can see the formula. It tells me my start value is 3, and then I just keep adding 3. And we all know how to do that. If you couldn't add 3, you wouldn't be in this class. And over here, it's no different. It's exactly the same. Generate a sequence given the following recursive formula. Well, I look at the formula. First thing it tells me is t of 1 is 3, so my start value or first term is 3. Then it says, and then multiply by 3. 9, 27, 81, 243, some large number. If you're going, those 4 things, those 4 skills, I got that. Then you're good. You're solid on this. And the only thing we're going to throw at you next class is an explicit formula. And the explicit formula is the equation. It's a formula because it's discrete. It gives us discrete values as opposed to the equation, which gives us a smooth line. And we need t of 0 for the explicit. The explicit is t of 0 and my rate of change. That's it. You always only need your start value and a rate of change. We'll look at those, and then we'll equate them to the actual equations if we were to connect all those dots. Just like I did on Desmos when we put the curve in there, and then we created an equation, a line of fit that connected all those dots. That was an equation. So that's what we're doing next class. Questions on this up to this point?